Welcome back to Physics Fundamentals. In this video, I want to go through some area and volume formulas. I'm also going to talk a little bit about how I use formulas in my problem solving and how I write things out in a way that makes it easier for me to use formulas in my problem solving. As with many of the review topics in this course, depending on your background, these may all be things that you are very well familiar with. These may be things that you have heard of, you remember having done, but it's been a while since you've thought about, or these may be things that are completely new to you. I don't know what your background is. The whole point of these first couple of videos is to make sure we're all on the same page going forward. Let me get my head out of the way and let's go through quickly. I'm not going to go that much into detail into what these shapes are, what they look like, but just a couple of formulas that you should be familiar with. For a rectangle, if we call one of the sides of the rectangle the length and the other one the width, the area is the length times the width. Of course, the defining feature of a rectangle is that the four sides are all right angles. A special case of a rectangle is a square, which not only has all four sides being right angles, but also all four sides having the exact same length. We generally call that the side length S. And so for a square, the area is just, well, it's the same formula as a rectangle, length times width, but it's S times S, and S times S simplifies and can be written as S squared. Up next, I want to talk about a triangle. And I'm going to draw a couple of figures here, because triangles can come in all sorts of different shapes and sizes. In general, we're going to have some side that we're going to call the base, B, and then we're going to very carefully measure perpendicularly the height h from the base to the furthest point. And the area is 1/2 base times height. The same thing is true if you happen to have a triangle that has a right angle in it. Well, then the height is actually the side of a triangle, which is a little bit weird, but nothing wrong with that. And then finally, if you have a triangle that is drawn in such a way that the point is way away from the edge of the triangle, well, it still works the same. You have to extend the line of the base outward so that you have a place where you can draw the perpendicular, but you still have a base and a height, and the area is still 1/2 times base times height. A parallelogram is a figure, much like the rectangle, where opposite sides have the same length. Let's call them A and B. But unlike a rectangle, a parallelogram does not need to have right angles in its corners. It can have any angle. And because of that nature of it falling down, we have to take the perpendicular distance that we will call the height, and the area in this case is the base times the height. A classic thought experiment on geometry here is, think about this triangle that is formed over here. If you take that triangle and move it over there, then all of a sudden you have a rectangle, and that rectangle has a length b and a width h. So that's where that formula comes from. A trapezoid is another very general name for shapes. When you first hear of a trapezoid, you're generally given a figure that looks something like this. The key idea of a trapezoid is that there are two sides that are parallel to each other. So no matter where you take the perpendicular distance between them, first of all, it's the perpendicular distance to each of those, and second of all, it's always the same. But we'll call one of those sides B1, we'll call the other one B2, and the area is going to be the average, B1 plus B2 over 2 times the height. I've seen this written sometimes as 1/2 times B1 plus B2 times H, and while that's mathematically the same thing, I really like this version because it emphasizes, what are we doing? We're taking the average value of that height. Because if you think about it, right, here's some average value of that size, and if you try to draw in a trapezoid, you get the same triangle thing going on here and here that you had with the parallelogram, turning it into a rectangle. So you take that average value, you multiply by the height, and you get the area of the rectangle. Right, I'm running a little bit low on space, but I do want to draw a couple of other trapezoids. I think it's important to realize that a trapezoid doesn't have to be sloped outward like that. You can have both sides of the trapezoid sloping in the same direction just by different amounts. It's still a trapezoid. The side on top is larger than the side on bottom. It's still a trapezoid. Or you can even turn it on its side. You can make one of the sides have right angles, in which case the side between those right angles is actually the height. You don't have to look for something inside. It's still a trapezoid. All right, the last two-dimensional shape I want to talk about is the circle. A circle is defined by its radius, the distance from the center to the edge, which is the same no matter which angle you choose to move in. And the area of a circle is pi r squared. I'll also mention here that we can talk about the diameter, the distance from one side of the circle to the other. Mathematically, the diameter is not very useful, but practically speaking, if you have a circular object, you can directly measure the diameter. You can't directly measure anything else. So, you take the diameter, you divide by half, you get the radius, and you can actually plug that into that formula. And it turns out that the area of a circle can also be pi over 4 times the diameter squared. Is that useful? No, honestly, we almost always use pi r squared because we want to deal with the radius. But it's worth mentioning that that is a thing we can do. All right, moving onward, let's talk a little bit about volume. I'm not going to do that many shapes for volumes here because, well, honestly, there's just too many. Generally speaking, if it's not one of these couple of shapes, I probably don't expect you to know it. All right, so we have here a rectangular prism. The dimensions there are the length, the width, and the height, and the volume is just length times width times height. We have here a cylinder. A cylinder has a circle at the top and bottom. We will talk about the radius of that circle. And then a cylinder has a height. And the volume here is pi r squared times height. One of the things I want you to notice about this formula, in both the case of the rectangular prism and the case of the cylinder, you're taking the area of the base of it, the thing that it's sitting on. Length times width for a rectangle, pi r squared for a circle, and multiplying by the height. That is the general rule for a three-dimensional object. And then finally, a sphere which does not have a nice base like that, the volume is going to be 4/3 pi r cubed. Like I've said, there are tons of geometric figures in 3 dimensions. Right? I could do cones, I could do pyramids, I could do domes, I could do parts of cones. There's all sorts of things I could do, but if you know these 3, you know everything I expect you to know. If you don't know them, have them on hand in ready references. So here is a relatively straightforward problem dealing with geometry. The volume of a cylinder is 250 milliliters. If the radius of the opening of the cylinder is 4.00 centimeters, how tall is the cylinder? All right. And so, I want to show you how I approach solving a problem like this. The first thing I realize is that I know a formula that is useful for this problem. Because of that, I immediately start dividing up my page and getting ready to work. I draw a line, roughly about 1/3 of the way across the page. So 1/3 on the left, 2/3 on the right. On the right, I write down the formula that I think is going to be useful. The volume of a cylinder is pi r squared h. Then, on the left-hand side of this line, I start writing down the variables. In this case, that's pretty simple. There's only a couple of variables. Right? There's v, there's r, and there's h. If I'm not sure which formula is actually going to be useful, I'll write down several formulas on the right-hand side, and I'll write down all of the variables for all of them on the right-hand side. Once I've done that, I'm going to go back and start looking at what I know. The volume of the cylinder is 250 milliliters. I'll go ahead and record that as the value of V. The radius of the opening of the cylinder is 4.00 centimeters. I'll go ahead and record that for R. How tall is the cylinder? The height of the cylinder is unknown. I'm going to go ahead and put a question mark there because that's important that I know what I'm looking for. once I have all of this written down, there's a couple of steps I want to take from here. I want to look at the variables. Ideally, there is one question mark, nothing blank, and everything filled in. That's exactly what I have, right? There's 3 variables, 1 question mark, the other 2 are known. If that's not what I have, then I have to really start thinking about the mathematics of what I'm going to be doing. If there's a bunch of blanks, well, maybe they relate to formulas that I wrote down that I don't actually need, in which case I start crossing some things out and hoping that I can make everything happy. I don't erase, I cross out, because if I cross out something that I end up needing, then I can rewrite it once I realize I needed it. But sometimes solving a problem is going to require using 2 or 3 or 4 formulas. That's okay. In this case, though, we're in pretty simple territory. The other thing I'm going to look for is my units, and I'm going to make sure that everything is going to be consistent. Right. In this case, I have 2 parameters. One is in milliliters and the other is in centimeters. Right. Those are not the same units, but I do know a relationship between them that's going to make them look more similar. Right. I know that 1 milliliter is 1 cubic centimeter. It might be useful to me if I rewrite that as 250 cubic centimeters. Now I have units of centimeters and cubic centimeters, and that makes me happier. That's going to make things easier when I go to try to solve the problem. The next step is contentious. There are people who argue with me about this step, and to some extent they're right. The next thing I'm going to do is rearrange my formula to solve for the unknown variable. Technically speaking, this is not necessary. For a lot of students, it's easier to plug in all of the numbers now and then start rearranging the equation from there. It makes more sense. And you won't go wrong by doing that. But it's rare in practice to have a situation where you only have to do this once, right? We're looking at a very artificial circumstance of me writing down this one problem and us trying to solve it. In a practical application, this is something that you're going to be looking at where you have to do the same experiment multiple times. You have to plug in data from every single test into the formula, and then you'd have to solve the equation every single time. And that sounds painful. So it's a good habit to get into that you rearrange the formula first and then go from there. That's what I'm going to do. So I know that h is my unknown. I want to rearrange the formula to solve for h. I'll start off by just swapping the left and right hand sides, because we're generally happier when the variable we're solving for is on the left-hand side of the equation. It doesn't have to be, but it makes us happy, so we go with it. I notice in this case it's a fairly simple formula. H is being multiplied by pi r squared. So to get h by itself, I want to divide by pi r squared on both sides of the equation. Now I have a formula that has h by itself. I'm going to move across the page so I can leave everything on. If I was writing pencil and paper, I'd probably be moving down the page. My page is landscape, so I have a lot of width that I don't have when I'm writing on a piece of paper. But at this point, I am safe to start plugging things in. V is 250 cubic centimeters. I know that pi is 3.14, but I'm going to go ahead and just leave it as pi, because I'm going to use the pi button on my calculator. And then r is 4.00 centimeters. I could do this whole calculation at once if I was very careful in using my calculator, but I'm going to work through it line by line just to make sure that I don't make any mistakes with the units, just to make sure that I don't make any mistakes with entering it into my calculator. All right, so I want to take 4.00 and square it. I get 16. All right, but 4.00 had 3 significant digits. When I square, I should keep the same number of significant digits. So I'll write that as 16.0 to have 3 significant digits. And then when I take centimeters and I square them, I get square centimeters. Right, that's useful. Now I want to take that 16 and multiply by pi. I'm using the pi button on my calculator, and that gives me 50.2654, etc., etc., etc. My calculator has like 20 significant digits of pi programmed into it, so the limiting factor is the 16, which had 3 significant digits. And so I'm going to write that down as 50.3. Pi is unitless. 16 had units of square centimeters, so my units here are still square centimeters. One last step. I want to take 250 and divide by 50.3. When I do that, I get 4.97. Although I guess 250 up here only has 2 significant digits, so I'll round based on that, and this would round up to 5.0. Then I have cubic centimeters divided by square centimeters. 2 of the factors of centimeters cancel out, leaving me with just 1 factor of centimeters, which is in the numerator, and the measurement I get here is 5.0 centimeters, which seems reasonable, right? First of all of my measurements are kind of in scale with each other. 4 centimeters and 5 centimeters seems like things that you would see on the same cylinder. If I had gotten 4 centimeters for the radius and I calculated 2,000 centimeters for the height, I would start to scratch my head and say, did I get something wrong somewhere? The other thing that's important, because my radius was given in centimeters, I kind of expected my height to be measured in centimeters, and by carefully following the units, that's what I got. All right. So this is the basic idea. This is what I want you to think about. This is how I want you to think about organizing your work when you're going through a calculation like this. I think that's far enough for this video. As always, thank you for joining me. I'll see you next time.